All right, everybody. In this video, we are going to introduce our parameterized surfaces. Now, we've already seen parameterized curves, and I'll remind you about what those look like here in just a moment. But parameterized surfaces are exactly what you would expect or what the name sounds like. It is going to be a two-dimensional surface in three-dimensional space. So think of that as, say, the surface of a sphere or the image given by the graph of a multivariable function, but it will be parameterized in a certain way using, in this case, two parameters. But let's not get ahead of ourselves. Let's start by briefly recalling what parameterized curves look like. And so a parameterized curve, and here I'll do it specifically in three-dimensional space. A parameterized curve was a vector-valued expression x of t, where here t was our single parameter, often representing time. And the output was three different coordinates, x, y, and z, each of them depending on that parameter. So a time-dependent x of t, y of t, and z of t. And then as we let t go in some range, so let's keep it general. Let's just say t goes between a and b. Well, then we would start at one endpoint. So this would be x of a. And then as we go forward in time, or forward in our t parameter, we could imagine tracing out this curve in three-dimensional space. So we might end up with something like this, and we would end at x of b. So again, our parameter is t, and we often visualize this as a time dependency. So we often imagine a particle or a little bug tracing out this curve as t flows forward. But we also have this understanding that the curve itself is being parameterized according to this variable t. All right, now with that, let's take a look at a parameterized surface in three-dimensional space. Now, a parameterized surface is going to be a similar expression. You'll notice there are two parameters, u and v. And so u is going to be a parameter, and then also v is going to be a parameter. And we have our x of u comma v. I will specify, because I don't think it's clear, we will often use the x as a capital letter X for a parameterized surface. So capital X of u comma v. And now this is, again, just a vector-valued expression. There are two parameters, so two inputs, but there are still just three coordinates as outputs. So an x, y, and z, depending on u and v. Now, how does this give us a surface? Well, I want to imagine what happens if we were to, let's say, fix our v value. So we just keep a very fixed value of v, let's say v equals 0 or v equals 1 or something like that, but we'll just keep it as a fixed number, and we let u vary. So if v is fixed and u varies, then what we get is an expression x of u, y of u, z of u, for this one fixed v value. And this is exactly what we saw up above. This is just another parameterized curve. So for a fixed v value, let's pretend it's just v equals 0. We might get a single curve here. So v equals 0 and u varies. U varies from its starting point to its ending point. If we were to pick a different v value, so let's say now not v equals 0, but v equals 1, we would have a different point. This is going to be x of u comma 1, y of u comma 1, z of u comma 1. So it's a different point in space. But again, as v is fixed and u varies, we might trace out a slightly different parameterized curve. And so this is going to be v equals 1. And we can do this for a bunch more. You can imagine v equals 2. No, actually, I'll stop there. But taken together, all of these curves that we get in three-dimensional space for a fixed coordinate v And then as u varies, these are going to be our coordinate curves. And these are specifically coordinate curves for our u variable. So these are often called our u coordinate curves because our u is varying for a fixed value v. But we could, of course, play the same game for v. So what happens if we let u be fixed and we let v vary? So let's pretend that we fix u to be 0 and we let v vary from its starting point to its ending point. Well, in that case, we might end up with a curve that looks like this. And this would be the curve u equals 0 and v varies. Right? And that's just x of 0 comma v, y of 0 comma v, z of 0 comma v. And so that becomes a curve, but it's a v-dependent curve. So v is the parameter there. And then I'm going to draw a bunch more here in sort of rapid succession. So as we choose different v values, we might get different coordinate curves. And these would be our v coordinate curves. And so we might get a picture that looks a little bit like this. Let's pretend that this goes all the way up to, what did we say here? So u is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's pretend that this goes up to u equals 9 and a varying v. So what we get here is sort of this patchwork quilt looking structure with all of these u coordinate curves slicing against all of these v coordinate curves. And I'll just write up v coordinate curves here to complete this picture. And in this specific example, we would say that u is allowed to vary from 0 to 9. And maybe we would write that over here, 0 less than or equal to u, less than or equal to 9. And v is allowed to vary. In this case, we went from 0 to 2. So 0 less than or equal to v, less than or equal to 2. But more broadly, just like previously, we let t go from a to b and be some interval in our t space. Here, we're going to let our u's and v's vary within a given domain in the uv parameter space. V space. So in this case, it is the rectangle 0 to 9 cross 0 to 2, but you could imagine some other theoretical domains as well. And so this gives us a surface, and we can imagine the surface as being stitched together by these different parameterized curves, these parameterized coordinate curves. All right, and so we'll see many examples of parameterized surfaces. In the video, I just want to introduce one broad type of example, and that is the type of example that we'll get when we build surfaces out of pre-existing coordinate systems. So typically either cylindrical or spherical coordinate systems. And I say this is examples. There are many examples here, but I will talk through one specific example with the cylinder. So if you remember our cylindrical coordinate systems for x, y, and z, we had x was r cos theta, y was r sine theta, and z was just equal to z. So when we're talking about coordinate systems, this was sending our Cartesian coordinates x, y, z to our cylindrical coordinates r theta and z. Now, what I'm going to recommend we do if we want to think about a parameterized surface of some sort is we're going to take one of these variables, so the r, the theta, or the z, and we're just going to fix it. So we're going to make it not a variable, we're going to give it a quantity. And so let's fix r, I think is probably the favorite to start with. Let's fix r and let's make it just the number 3. So everywhere up here, I'm going to fix it with a 3. And notice now I only have two variables. I have theta and I have z, and I'm going to let those things be my u and my v for my parameterized surface. So we'll let x be equal to 3 cosine of u, we'll let y equal 3 sine of u, and we'll just let z equal v. And so taken together, this is going to give us a parameterized surface, call it capital X of uv, equals, and then for our x coordinate, we've got 3 cosine of u. For our y coordinate, we've got 3 sine of u. And for our z coordinate, we've just got v. Right, so again, if we're trying to build a surface out of a pre-existing coordinate system, either cylindrical coordinates or spherical coordinates, I'll choose one of those coordinates and just give it a fixed number. And the other coordinates, in this case theta and z, I'll let be my u and v from previously. So this gives us a parameterized surface, but what parameterized surface is it? Let's check our coordinate curves in three-dimensional space. And I'm going to see what I can do to graph this semi-reasonably. Right. So for our first coordinate curve, let's call it our u-coordinate curve, which means that we are fixing our v value. So our u-coordinate curves are going to all allow u to vary, and we'll fix our v. And so these will be curves in three-dimensional space. We can think of them as 3 cosine of u, comma 3 sine of u, comma, and then we'll have just a fixed v value, so I'll just call that v naught to indicate that it's fixed. And so for a given v naught, let's say v naught equals 0, what we're going to get is 3 cos u, 3 sine u, 0. And that is just going to be the circle of radius 3 positioned at height 0. And so we might get something that kind of looks like this for our v naught equals 0 coordinate curve. And then similarly, if v naught was equal to 1, we would get a circle of radius 3 situated at height 1, because the parameterized curve would be 3 cos u, 3 sine u, comma 1. And so that would be v naught equals 1. And then let's do one more. Let's let v naught equal 2 up here. So we'd get a circle of radius 3 at height 2. And so these u-coordinate curves are circles of height v naught and radius 3. Great. What about our v-coordinate curves? Whoops, and I'll switch to purple to keep the coloring consistent. So for our v-coordinate curves, that means we're fixing our u value and we're letting v vary. And so for a fixed u value, this would be 3 cosine of u naught, 3 sine of u naught, v, as v is allowed to vary. And so for a given fixed u naught, we're really fixing our angle here. So if u naught equals 0, we're looking at angle 0. And then as v is allowed to vary, the only thing that's going to change here is our z coordinate. So we're going to end up going straight up. And that might correspond to a v coordinate curve at u naught equals 0. And at u naught equals 1, no, sorry, at u naught equals pi over 2, we'd be over here. We're going to pretend these are all stacked on top of each other nicely. As always, pretend my pictures are good pictures. And this would be our u naught equals pi over 2 coordinate curve. Then we have this one in the back here. So that's going to be at the coordinate curve at u naught equals pi. And then at 3 pi over 2 will be over here. But in general, for any given u naught, we're going to get this straight vertical line. And what we realize is that this entire parameterized surface is really describing a cylinder. It's specifically a cylinder of radius 3, which makes sense when we think about our original choice of the number 3 here. And so we get a cylinder of radius 3 whose coordinate curves are circles and vertical lines, respectively. And if we had, picked a different starting point instead of fixing r, if we had fixed theta or we had fixed z, we might get different surfaces as a result. So this is our introduction to parameterized surfaces, two-dimensional surfaces in three-dimensional space, which can be thought of as being woven together, stitched together with these different coordinate curves, which are themselves parameterized curves in their own right. So that's all I got for this video. Thanks so much for watching. See you next time.